This is the screencast for section 7.1, example 4, modeling the effects of acceleration. So now we're going to look at a car, and this car is moving with an initial velocity of 5 miles per hour and accelerates at the rate of a of t equals 2.4 t miles per hour per second for 8 seconds. Well, part A is asking us how fast is the car going when the 8 seconds are up, and we know that cars travel in miles per hour, but here's why. Acceleration looks at the rate at which the velocity changes, miles per hour per second. Well, remember, velocity change equals acceleration times time applied. In other words, dv equals a of t times dt. So we can integrate that. So v of t, my velocity curve, is going to be the antiderivative of a of t dt. Well, I want to find that over a span of 8 seconds, and the acceleration curve is 2.4 t. Now remember, that would just find the displacement, the total change in velocity. We started out, though, with an initial velocity of 5 miles per hour. The problem wants to know how fast the car is going, not what's the difference between the speed at 0 and 8 seconds, but actually how fast it's going. So we're going to need to add 5 on because we started at 5 miles per hour. Well, now we're going to take the antiderivative, which is weird. You usually see the 5 on the inside of the dt, but now it's on the outside. Really, you can't put the 5 on the inside of the integral because then you would have to, when you take the antiderivative, be multiplying 5 by t, and we shouldn't. We're just adding 5 at the end. That's why it's not involved in the antiderivative. But at this phase, it would be the same as plugging in 8 and then plugging in 0 because 5 doesn't have a t. So now I'll use fundamental theorem part 2, plug in 8, plug in 0, and then of course adding my 5 at the end. And after some simplification, I get that the car was traveling at 81.8 miles per hour. The displacement was 76.8 miles per hour, so at time, the difference between time 0's speed or velocity and time 8's velocity was 76.8 miles per hour. So it increased 76.8, but from 5, so it was going a total of 81.8 miles per hour. Now part B asks how far did the car travel during those 8 seconds? How far is a position? So far we know that acceleration is 2.4 t. Then we learned that velocity is 1.2 t squared plus 5. Remember that plus 5 isn't part of the antiderivative of velocity, it is part of the velocity curve itself. The total velocity is the antiderivative of acceleration plus the initial value, 5. So 5 was kind of like our c value here. So now position is going to be the antiderivative of our velocity curve, 1.2 t squared plus 5 dt, and it wants to know how far the car traveled, so we're going to use absolute value, the total distance. Now, fortunately for us, this graph of velocity is a parabola, so all the distance is going to be positive anyway, so we don't really have to worry about those absolute value, which is kind of nice. So now I can just take the antiderivative, use fundamental theorem of calculus part 2, simplify, and I get 244.8. Now be careful, 244.8 is miles per hour seconds. Remember, when we went from acceleration to velocity, it was miles per hour per second, and then we multiplied by seconds to get velocity, so just miles per hour, and now we're multiplying by seconds again, so now we're at miles per hour seconds, which is weird. So I'm going to write that in a different way. I'm going to say that's 244.8 miles per 1 hour times seconds, so miles per hour seconds. And I'm going to convert because I know that I want my answer to be in miles. So I'm just going to use a unit conversion here. There's 1 hour in 3,600 seconds, which is nice because then hours cancel and seconds cancel. And I get 0.068 miles, which you can pretty much conclude that this car traveled a little over half a mile in 8 seconds. So is it going very fast? Well, it's going 81.8 miles per hour, so yeah, it's traveling fast. Did it accelerate fast? Well, it accelerated at a rate of 2.4 miles per hour per second. Now try problem number 9. Says an automobile accelerates from rest at 1 plus 3 square root t miles per hour per second for 9 seconds. What is the velocity after 9 seconds? Okay, so the velocity is going to be the antiderivative of from 0 to 9 over the 9 seconds of the acceleration curve. Fine. And then we have to add on our initial value, kind of like our plus c value, and it was from rest, so that's going to be 0. So now I can do a little bit of integration, and then fundamental theorem of calculus part 2, and then I get 9 plus 54, and that's going to be miles per hours per second. That was the acceleration, and now we're multiplying by time, so that's seconds. So that's why, again, we end up with 63 miles per hour. Now part B, how far does it travel in those 9 seconds? Well, the position curve is going to be the antiderivative of the velocity curve. Now remember, our c value was 0. So if our initial value was like 3 or something, I would have had plus 3 inside the absolute value here. Again, this curve is all above the x-axis, so I don't need to worry about the absolute value. It's not going to change any negative area to positive. So now, remember, when velocity is negative, the car is moving backwards. So this car moved forward the whole time, basically, so we don't have to worry about the absolute value. So now we're going to integrate, use fundamental theorem of calculus part 2, and now I get something miles per hour and then again times seconds. So we took the velocity times dt times seconds. And I get 234.9 miles per hour seconds again. So I know that distance is supposed to be in miles. So let's convert. There's 1 hour in every 3,600 seconds. So that's 0.065 miles.